All right. All right. Hello, everybody. You're in a call with Current Continuation, which is a podcast. This is the second episode, and we're really happy to introduce Satnam Singh. He is currently a fellow at Groq. Groq is an AI chip company that deploys LLMs at scale, and it's really fast. At least that's what they say on Twitter. I've never used it. And before that, he worked at Google, at Facebook, and at Microsoft. And a long time ago, he was also an academic, and he received his PhD from Glasgow. And he works on really interesting stuff at the intersection of hardware and programming languages. So we're really excited to have this conversation with Satnam. So thanks for joining us today, Satnam.
Pleasure to be here. Thank you for having me.
Yeah, so maybe we should start with at the beginning, right? Like you've had an interesting upbringing, and so tell us about how your life.
Well, my life started in India, in Punjab, northwest India. Uh, and when I was one and a half, my mother and I moved to Glasgow in Scotland. So I grew up in Scotland, even though I was kind of born in India. My father had gone ahead to pave the way for us, and I kind of grew up in a kind of a Sikh Punjabi speaking family. And I turned up at elementary school, age 5, not speaking any English. So I was put to some special track for a couple of years to learn English before I was reintroduced to normal tracks. My parents always spoke Punjabi, and I didn't speak any English. In fact, they couldn't even read or write Punjabi because they were both illiterate, didn't have any education. So it's a bit odd because in my family, I was the first person that went to like elementary school, high school, undergraduate, PhD, became a lecturer or professor, as you Americans call it, etc. So that's kind of, where I kind of come from, and I I got into computers at high school. In high school, I was quite interested in physics, and the physics teacher, Mr. McClure, he really took me under his wing, and he made me join the chess team because I was reasonably good at chess. So I played in chess competitions, and after school, he had a computer club. So this is like in the late 70s, early 90s, and the kind of computers that we had were things like Sinclair ZX80 computer, ZX Spectrum, ZX Spectrum computer, and a BBC microcomputer, a 6502 based computer. And I just fell in love with these computers. I couldn't, they seemed like magic. You typed in some basic, you ran it, and things came up on the screen. And what captivated me was that I just couldn't understand how this could work. How is it you type these things, you ran it, and some computation happened, or some string got written? And I just persuaded my parents to try and get me a computer, which was tough because I came from a pretty poor family. My father was a construction worker, then he'd end up in welfare, so we didn't have a lot of money. And so what I did was I convinced my parents to spend the money the government would give them to buy me a school uniform. So although I went to a state school, it still had a school uniform requirement. So instead of using that money to buy a school uniform, I said, buy me, help. I want a BBC Micro 8 model computer, and we got a free school uniform from the local charity shop. So I just spent my teenage years writing BBC Basic, 6502 assembly, BCPL, trying to implement wee mini compilers, mini operating systems. So that's how I ended up in kind of the world of computing. And then my only, as an immigrant in the UK from India, my only path forward was education. I wasn't going to work in my auntie's insurance company or my uncle's second-hand car sales company or whatever, because we didn't have any connections to the community. So, what's good about the UK was uh, I had grants to support kids from poorer families. So I didn't have to pay anything for my university education or my books. I got some allowance. So both my undergraduate and my PhD were paid for by the state, which was an amazing thing about the UK government at that time, because I don't think I would have gone to university otherwise. So that's how I ended up in computing in education from a background of immigration.
So, do you mind if I ask, just because you mentioned in passing programming in 6502 assembly, which of course totally makes sense. How did you where did you find the book? Like, did you check it out from the library? Did you like
So I wish I had had a with me as a prop. So on the BBC microcomputer, it comes with a user guide, the BBC Micro user guide, and it has everything about BBC Basic. It has the schematics of the board, every chip, every detail, and BBC Basic has an inline assembler. So you write basic and then you drop into 6502, and then you can use some of the variables from the enclosing scope from the basic. And then you could do a multi-pass compilation by having a for loop where you compile several times to resolve the forward, backward symbols, etc. So I learned it from the book. I did then buy more. There are some official BBC 6502 programming books, and I bought them to learn how to do more 6502 programming. But from the book, just even from the BBC Basic User Guide, you can learn quite a lot.
It's amazing.
Computers don't come with manuals these days, yeah.
Totally.
Yeah. I love the fact that this computer, it came with a user guide which told you everything about the computer. It had the operating system's memory map. But if you want to try an A on the screen, how do you do it? Well, LDA #65. That's capital A, GSR FFEE. You jump to that point, and then an A will get rendered on your screen. So every kind of detail was described in this book. Or you want to create a special bit of circuitry to do some music synthesis, whatever. You create a wee circuit board, and you connect it to the special serial parallel port under the machine, and it has the spec of all the wires and the voltages and the protocol, and you could code it up. And that was like an amazing thing. One thing I love is breaking the distinction between hardware and software. It's just a system. It's just an end-to-end system. And this user guide, I think, had that kind of philosophy, is that you have this box in front of you that computes. Here are the things you need to know about how to make it compute. And those things, they cross hardware and software. Programming 6502, how to program the Hitachi 8645 video controller, how to program the PAL teletext chip. It was all described, and it was all available to you. And I missed this intimate connection with the hardware that I had in the BBC Micro, because today we have so many levels of virtualization, abstraction between the program we write and the reality of how it executes, and the reality of which way the electrons go at the transistor junction.
All these pesky operating systems and virtual memory and all this really get in the way.
Yeah, and hypervisors and all kinds of things like that. Yeah, and even and 652 is a very simple processor. When you wrote your code, you know how many cycles it would take to execute, and you had some feeling about the economics of that execution. Today we have these ISAs for x86. Our compilers generate these x86 instructions. Those instructions are very, very, very faintly related to the actual instructions that get executed in your processor core. And how many cycles will it take to execute? Well, you have no idea about that. That's a very complicated, sophisticated thing. So an ISA, is now like a contract between the world of compilers and the software stack and the people that implement hardware. A contract abstraction, which I think is under stress as we now have these kind of multi-core processors and heterogeneous computing, and we're being forced to get performance from paths other than the scaling expected through Moore's law. And the world of heterogeneous computing is stressing that ISA abstraction.
Totally. So if you don't mind returning to this sort of like chronological view, we were wondering also, you perfectly described how you got into computing in the first place and into programming. How did you decide that grad school was for you? That's not necessarily given, even for someone.
So I went to university. I originally studied physics, which I was very interested in physics. I thought I wanted to be a physicist. I wanted to do nuclear physics. I wanted to work at the Deutsches Elektronensynchrotron in Hamburg. I mean, not only did I study physics in high school, I studied German because I thought I was going to end up in Hamburg, and I did very well at physics at my high school. But just like everyone else in my physics class, in the Kelvin lecture theatre at University of Glasgow, where Lord Kelvin used to give his physics lectures. But everyone else was top of their class as well at high school, and now I'm realizing, I am not necessarily going to be the top of this class. And I did fine in physics. I got pretty good scores, but I kind of had to work quite hard on it. And I had to pick a third subject, and I picked computing, not expecting to graduate from it, just as I don't know what the American term would be, elective. And what I observed was I got nearly 100% in computing and didn't require much effort. The physics, that was hard. So then I switched degree my second year to do a joint degree between electrical engineering and computing science and computing and electrical engineering. So I changed path. But I was really, I always thought I wanted to do a PhD because at school I worked out how do I become a nuclear physicist. And I sort of like send letters back then, there was no email. And the physicist that would reply to me would say things like, well, Satnam, if you want to become a physicist, the first thing you want to do is get a PhD in physics. And before that, you need to get a degree. So even at high school, I kind of knew what a PhD was before I knew what a degree was. So I kind of knew that was my kind of path, right? I was going to do undergraduate degree and then I was going to do a PhD. And then when I went to university, I was actually really inspired by some of my professors. Some of them were just so wonderful at teaching, they had such passion for the subject. I remember, specific people like David Watt's lectures on ADA and things like that. They were wonderful. And I thought, that's a very cool job. That's a very cool person. I want to be like that. And I started to question whether I wanted to be a nuclear physicist. Well, at that time, I already decided I was doing computing. So I fell in love with the idea of being an academic and being teaching, a collegiate environment, thinking deeply about problems. So I thought, yeah, that's probably maybe that's probably for me. So I was inspired by my professors.
And what was your thesis work on at Glasgow?
So
my final year undergraduate project was about creating a functional language to program these special kind of chips called PALs and PLAs. So they're chips which you could configure. You could download a bit stream. You could configure them to make some computation. And they have some general assembly of either a sum of product or product of sums and some inverters you could put in various places like that. And I don't know why I thought it was a good idea, but I thought, I'll just create a functional language. The problem is I created my own project.
So you went from coding in assembly all the way to functional. What was that like?
Well, I mean, to me, I just view it as just a progression of the same thing. So I thought it was necessary because I think what's missing in the world is a diagonal. In the world, we've got high-level things for solving high-level problems, Java, web interfaces, and low-level things for tackling low-level problems, assembly code C, right, for low-level systems. But I think a wonderful thing to have are high-level things to make you productive for doing low-level tasks. So that's what I wanted. I wanted to supercharge and make myself more productive at doing all this low-level stuff. Not give up control. I still want to control the hardware that's made and its economics and its performance. I just want to be more productive at doing that. So I felt that there was some natural synergy between functions and how circuits work, right? They just seemed well matched to me. So I don't know why, but I kind of hacked up this language. I mean, I knew nothing about languages. I was a final year student, but I hacked up a language. I even remember what it was. I called it Pineapple for some reason, and wrote a recompiler for it. So you could write these recursive functions and to describe it's kind of smallish to medium-sized logic blocks, and I would analyze it, and then I would generate the programming bit stream to program these PAL and PLA chips. And I kind of loved that, and I think the project went very well. And then I knew I'd want to do a PhD. And I applied to several places for PhDs. I got rejected from most of them, but I got two offers. One was at University of Edinburgh with Robin Milner, and the other was staying at Glasgow with Mary Sheeran, who had been my final year computer architecture professor. And one reason I went to Glasgow, University of Glasgow, is I actually grew up pretty much on campus. My high school was on the university campus. So when I sat in my high schools, I could see the university tower outside the building. The electrical engineering department's on the same street, like two blocks down. So I had a small view of the world, probably because of my kind of Punjabi immigrant child upbringings. So I just assumed that you just went to a university that happened to be on your school's campus. So I just applied to Glasgow. I just applied to Glasgow. I don't think I applied anywhere else for undergraduate education. And then when it came to the PhD, I was offered these, I had these two options. And Edinburgh, 40 miles away, seemed like a vast distance. I could not imagine going that far away from home. And I stayed at home. When I was undergraduate, I lived with my parents. It was just like a 10-minute walk to school. So still a 10-minute walk to the university. The university is the same place my school was. So so I thought about it. And then the other thing about Edinburgh was these professors, like Professor Milner, Professor Bristol, seemed amazing people. They had this idea. They had an idea for a project for me, which was to work on a parallelizing compiler for standard ML. And that sounded pretty interesting. But he showed me where I would sit if I'd be a PhD student. And this thing, it wasn't even really an office. It was more like a cupboard. And it already had 2 PhD students in it, and I would be sort of crammed in between them somewhere in this kind of grey monolith in the south of Edinburgh. Whereas at Glasgow, I was in these beautifully converted Victorian buildings with stained glass windows, with spacious rooms for the PhD students, and it was 10 minutes from my parents' house. So I still stayed with my parents when I started my PhD, and I decided to do a PhD with Mary Sheeran. More fun with functional programming and hardware design. So I was quite inspired by Mary's final year lectures on computer architecture, but described in a kind of more formal, symbolic, functional kind of way. And I remember my lectures about transputers and Occam. So I just loved all this synergy between a way of computing some architecture and a way of modeling and programming it. And when you seem to get a really good impedance match between the two things. So I was captivated by all these things that Mary lectured about. So I signed up with Mary. I signed up with Mary instead. And I was her first PhD student. I think my life would have been quite different had I done a PhD with Robin Milner. I often wonder what that'd be like, but I'm very happy with the choice that I made and the path I took.
So remind us, did Lava come from the PhD work?
No, not at all. Lava came a lot later. It came from when I worked at Xilinx. So my PhD, where I did work on functional language modeling hardware. At that time, there was Miranda was around. GHC had not started. So, I started my undergraduate in 1983 for 4 years, and then I started my PhD in 1987. So it was pre-GHC. So I used Miranda, and I absolutely love the fact that Miranda was an even better match for modeling hardware than this Pineapple thing that I had done before. And the reason for that was lazy evaluation. I could directly describe a circuit in the language and run it and give it some values, which I couldn't really do with other languages. And this is to do with state and loops. Because in Miranda, you could describe a state element simply by writing a function that took a list as its input. And at the output, you add an element to the front of the list, undefined, whatever, 0, and you cons it to the list you got at the input. That has delayed that list one step in time, if you consider each element of the list as being a value in time. What a beautiful way of describing what delay means. And then in sequential circuits, you want to have a value fed back as like a counter. So you take the previous value, you add one to it to get a new value. Well, you just write that directly. You can have the value, the x can be both sides of the equals. And because of lazy evaluation, the right thing happens. You give it a list of some finite size, and then you just take the finite size list at the output, and you get the answer. So you have this direct, kind of almost isomorphic representation of this physical thing in the world with a very light and beautiful small set of abstractions. And that just seemed wonderfully compelling and kind of magical to me. I really loved that. I thought, people often struggle to justify lazy evaluation because it comes with so many costs and complexities and difficulty for analysis. But when it comes to modeling things like state and feedback in digital circuits, I think it's perfect.
And I guess that's your connection to Haskell. That's where perhaps it started. And
well, so Haskell then, while towards the end of my PhD, I think Haskell was coming along, and so the kind of lazy evaluation and the kind of list processing functions that you write in Haskell are very similar to Miranda, because Haskell is like a version. is an evolution of evolution of Miranda. So my PhD, I built up this system where you could describe circuits using Miranda, and have multiple interpretations for circuits. Like think of them being overloaded. This is before Miranda didn't have type classes. They were being developed by my fellow PhD student Stephen Blott. Stephen and I were undergraduates together at Glasgow too. So Stephen worked for Wadler to do type classes, which will then find a way into Haskell. And I came up with some system which let me describe a circuit graph, and have one interpretation where you simulate it, another interpretation where you could compute the critical path, the delay through it, another interpretation where it could draw itself, another interpretation where it could compute testability vectors by composing other non-standard interpretations. So that's the topic of my thesis, non-standard interpretations for circuits. So capturing what's common across lots of different computations and abstracting that, and then instantiating it with the differences and then composing them. And that was inspired by the work I'd done this summer before at a silicon chip company called European Silicon Structures, where I was like an intern for 3 months, and I had to manually write these programs again and again and again. I felt like I've seen this before. This is the same pattern, and why am I rewriting the C++ again and again and again? And I felt that this is something that should be abstracted. So looking for these things that get repeated as patterns and turning them into useful commonly used abstractions, and then composing them hierarchically, that was the inspiration that kind of drove my thesis work.
That's very interesting. So I'm very far from hardware, so I don't have a good view of what the hardware design languages are like. I mean, I've used Verilog in undergrad, and that's where I stopped. So and you're describing these very sophisticated and interesting languages from the early 90s, late 80s. What has happened since then? It seems like they did make it
yeah,
great, right?
Yeah, so I have I feel that there's just a tragedy in the world of hardware. The languages we have, the mainstream language hardware, honestly, I just don't think they are fit for purpose. And they have very troublesome underlying semantics. And they were never designed to make hardware, designed to model hardware. So Verilog is the most commonly used language. I used VHD a lot because I was in Europe, and VHDL was much bigger in Europe. But they have similar kind of semantics. Their semantics are based on event-based simulation, because these languages were designed to simulate circuits, not to make circuits or create them. So they have event-based simulation semantics, which is completely sequential. So this is absurd. You have it's totally sequential model to try and simulate something that's inherently parallel, where every gate is running the same time as every other gate. At the same time, computer scientists are developing multi-threading concurrent programming for programs that run on one core. So their model is parallel concurrent, and they run it in something that's inherently sequential. And the hardware people have it the other way around. So this seems like totally mad to me. So I don't think a huge amount has really kind of changed. I mean, Verilog has morphed into system Verilog, but it's hard. It still has this troublesome vet-based simulation semantics. People have tried to make other languages for hardware design. I mean, I've tried to make my DSL Lava Xilinx, but it still works by compiling to Verilog. There's been great work done by the people at the company BlueSpec that made this fantastic Haskell-inspired hardware description language, which I used for one of the chips that I worked on at Google. And it's got very interesting, sophisticated types, lots of powerful abstractions, but it still works by generating Verilog. So the reality today is, if you were actually make a chip or design, you can create all these terms of abstraction, but the standard kind of API down to the gates is Verilog with its troublesome semantics and tooling and kind of sequential kind of model of the world. So during my PhD, I didn't actually get the mapped in real hardware. I produced this system that would compile to VHDL. You could run simulators. Then I was lucky to get a position as a lecturer, electrical engineering department at the same university. So after 7 years of study, I literally moved 2 blocks down the same street in Oakfield Avenue, because it was just like I said, adjacent to my high school. And I sort of settled into my office. And then the guy who was my manager at this ES2 company where I worked as an intern before my PhD, he'd started a new company in Edinburgh. He was a professor at Edinburgh, John Gray, and he created a new company. He created these new FPGA chips he was excited about. And he comes and visits me, and he sort of kicks my door in, and he brings me this very, say exactly this FPGA board. It's like, this is a PCI card. Some of you might never have seen an actual PCI card, no E in its name. It has these very interesting FPGAs. You can download logic onto these kind of Lego of hardware, and it will do anything you like. And it works. You plug it in, and it's into your memory space is a configuration state. So you can write a C program, and just by reading and write to memory locations, you could configure computations on this chip, execute them, and run them. So they've made this amazing board. They said, Satnam, I saw your PhD thesis. Interesting work, but come on, man, do something real. Here's a board, work out the program. I'll be back in 3 months. I expect you to have a working compiler. Storms off back to Edinburgh. So here I've given this card, and I've given this challenge because he's like a real electrical engineer here. He thinks all this kind of, Miranda Haskell stuff's kind of fine, but he wants to see something real done with it. So I tried to start to develop tooling and applications which exploit these chips. In fact, you could change the hardware as you could run. So this, and then I started to make programming abstractions for reconfigurable hardware. So imagine chips where you're swapping bits of hardware in and out, like virtual hardware, like virtual memory, except that you're doing it with hardware blocks. So I built a wee bit of a research career for myself doing that, mainly publishing in FPGA conferences, but trying to take ideas from worlds of programming and operating systems and virtual memory, but reimagining them in a world where you could change the hardware as it's running. The hardware itself could compute the next bit of hardware it is. So that's all kind of mind-bending stuff. And quite a lot of the 90s FPGA research was about how to try and harness the power of this dynamic reconfiguration. Because now you can have a circuit, a virtual circuit that's much bigger than the physical limitation of the chip. So that was another great forward step for me. I kind of owe John Gray a lot of gratitude for giving me a kick in the right direction.
So about that work, so about kind of transitioning to the FPGA world and Lava eventually, I mean, there's a lot of things that are really inspiring about Lava. Sometimes it's like a huge inspiration for many of us working on hardware design languages today. Something that I feel like is maybe underappreciated about it that is how few, like, or maybe in contrast, how few languages today have anything to say about the physical layout of circuits. That is, like, there's a lot of really exciting work going on in hard description languages and high level languages for generating hardware. Very little of it has in the semantics something about the kind of like the physical instantiation. We're just sort of like content living in this world of like a graph of the interconnections of components or something. And I'm just curious, like, what your thoughts on this are, in particular, like what the modern world should learn from this type of approach, where you get like kind of direct.
I'll say a wee bit how we got there. So first, I started off with a pre-version of Lava for programming this chip. And these chips are pretty small. They don't have that many computing elements. So you have to be very careful and frugal about how you lay your circuit out. And is this thing close to other things? You really want to control your critical path. So out of frugality and necessity, I had to come up with a model which was really aware of location. So at Xilinx, the reason that Lava got made was because we had customers who could not fit their designs into the FPGA chips. They picked a particular chip or a particular size, that's what they could afford. And they had some design, a FFT, a software-defined radio. They couldn't quite jam it in. And the field application engineers from Xilinx, they were helping the customers. They just couldn't get it. The tools all worked on place and route. Right? They take an abstract circuit netlist, they roll dice a lot, and they try and with simulated annealing, heating, cooling, try and see if it would go in, and they just couldn't get it to work. So it's only when people are desperate do they go to someone else and say, right, you've got this weird other stuff. Could you help me? Because we've tried every other thing and it has failed. And we're lying on the ground bleeding. So I kind of looked at the circuits. I saw, they've got regular structure, and the output of this segment of the convolver should go to the input of that segment for. And on the chip, this is how it should be laid out, and this is the wires it should use. This is the registers that should be used, and this should be a row, and this should be a triangle. So I just developed Lava to let me have this a composition by abutment as a concept, but also geometry, row, call, triangle, flip, etc. And by doing that, I was able to get the customer design to fit onto the chip. And it also looked beautiful. You could actually see the structure of the circuit that you drew on the whiteboard. You saw it on the actual chip. And it fitted and it met timing. It was fast enough, and you could ship it to the customer. So that's very satisfying. It's always great when you do research that is driven by trying to solve a problem, and it's a problem which no other current technique could solve. Right? People, you are the last recourse to law, as it were, from the regular engineers who would otherwise rather write in Verilog. So I think I kind of learned a lot about that. It taught me the power of developing high-level abstractions for controlling low-level issues. The low-level issues is placement, what is next to where? How long is that wire between these two blocks? What will be its critical path? Because it's the slowest, longest wire that determines the speed of the overall system. So you want to be productive and be producing low-level systems. And you want to be agile, because the first layer I produced didn't meet timing, or it didn't fit. So I had to experiment and try different decompositions, different layers. But because I had this tool which gave me agility, I could try 5 or 6 things in one afternoon to find the one that worked. That was a real superpower. And I could do that because I was productive. I had these high-level abstractions that made me productive, that let me explore more of a design space in an afternoon in a way that was just infeasible with VHDL or Verilog. I think that's quite exciting, and I'd like to see more of that in the world, more high-level abstractions that let you control low-level concerns.
It's pretty sweet. Yeah, and I wanted to ask about another paper of yours. So while preparing for this, I found this paper called "Checking Safety Properties Using Induction and a SAT Solver" with Mary Sheeran and Stolmark, and I was surprised because like it seemed to me when I saw it, and from the date of the paper, that was probably the first use of a SAT solver for verification. Is that correct?
Not at all. I think SAT solvers have been used for other kinds of verification. I'll give you one example just from my own personal experience.
Yeah, because from my view, it was like bounded model checking that kind of started using.
That's right. That's the point.
It came before bounded model checking.
Yeah. So I think
it wasn't unbounded too, so that was better.
That's right. So up until a point, there was bounded model checking, and that was very much driven, right? I think with the different representation, BDDs, right? Not SAT solvers. But I think SAT solvers did enjoy use in other types of verification. And one thing that's close to what I work on is logical equivalence checking, where you've got 2 digital circuits where one is maybe a slight mutation of the other, and you want to know, are they the same, right? So logical equivalence checking, LIC, it's a very common thing in the industry to work out these 2 circuits, and it can use SAT. It typically uses SAT solvers. It still uses SAT solvers, and the way that works is that you look at these circuit graphs and you match up where the state elements are, which is obviously quite a heuristic thing. It might require some human intervention. But once you would match the state elements in the 2 circuits, then you could just check using a SAT solver, just check the equivalence between all the registers. And if that passes, then you know that 2 circuits are the same. So they're a standard part of the tool flow in hardware design companies. Like, we run them all the time in our company. And all the main companies sell them. So I think that was one example of how SAT solvers were used for verification. What's perverse about that type of verification is this is a tool you buy from these hardware vendor tools. The typical way you use it is you use it to make sure that another tool you bought from the same vendor has not broken your circuit. So you write you give this your input to some tool that you're paying millions of dollars for. The tool runs, it produces takes one circuit graph, produces another circuit graph, but that tool could have had a bug in it. How do you know it did the right thing? So then you run, you get your cables out, you run a logical equivalence check to check that for that particular instance, is the output circuit, does it still have the same meaning as the input circuit? So that's like a weird kind of checking, right? You're not checking that a human designer made an error. You're checking that invocation of that tool didn't make an error. But I think there's lots of great uses for that kind of stuff. Like one thing that's top of mind for the moment is machine learning compilers and the transformations they do and possible mistakes that they might make. And there, I think, today, I think it's a great opportunity for technologies like eGraphs, eggs, to make sure, like, for example, in the MLIR framework, that the graph that comes in to one stage of lowering and the graph that gets produced, they have the same semantics, and you haven't introduced an error. So these things don't prove that your compiler is correct, but they can help you prove that for one invocation of your compiler for a specific input, perhaps there's a mistake the compiler that you might be able to catch when you do it. So yeah, there was some use of SAT, but I think that paper, I think, kind of led to a mini revolution in being able to do these unbounded proofs, right? And I think the algorithms in all the main model checking tools, Jasper, Gold, etc., etc. I run these tools occasionally, the USSHQ tools, and occasionally we'll check some property and it will say proved by K induction. And as my heart misses it, I feel happy with it.
That's cool.
That's awesome.
So should we shift to talking about career, Adrian? What do you think?
Yeah, totally. So like you are one of the academics in our community who has the benefit of having seen the industrial side from many different angles. As like we were obviously just talking about Xilinx a while back. You've also been at Microsoft Research and at Google. And so one thing we were just curious about is like what your sort of view on research and PL research looks like from that angle. In particular, like how has your life as a sort of like research connected person changed when moving from company to company? Like, were things very different going from Microsoft to Google, for example? How did you find this? We'd love to know what your life has been like going through all these things.
Yeah, all these transitions were very, very different, and but I'll say one. I'll give a general answer, and then I'll describe a few specific transitions. So, I feel very fortunate to have done a kind of PL-esque PhD in this fantastic group. I was in the function program group at the University of Glasgow. Started in '87, finished in '91, and that was when Phil Wadler had come, Simon Peyton Jones, Mary Sheeran, John Hughes, John Launchbury, and amazing collection of PhD students like Stephen Block, Simon Marlowe, Graham Hutton, etc., etc. So that was like a very vibrant, fantastic community to be in, and I love the collegiate atmosphere, and I love all the talks and the presentations. And what it did was it gave me a toolkit. Being a PL PhD student gave me a toolkit for how to think about problems, how to decompose problems into smaller problems, how to solve them, how to communicate a problem to someone else, how to read and understand information and then represent it to someone else, how to get feedback and change my plan. All of these skills that you learn as a PhD student, they're like an amazing toolkit for being a problem solver that have applicability way beyond programming languages. So it gave me like a philosophical view of how to work and how to interact with people and how to solve problems. And so that was invariant. I worked in all these different places and I did quite different things, from designing hardware to working on Kubernetes to Android apps. But I had this sensibility that is constant about how to think and work that helped me for all of these jobs. And whenever I give a talk, I just gave one just 2 days at Imperial College, I really emphasized to the PhD students, especially the PL ones, don't have a blinkered view about you only working on PL or compilers or becoming a professor or whatever. You're being trained to be a problem solver. You're being trained to have this general toolkit to look at technical problems and solve them, and communicate with other people and participate in a wider group of people to do great creative things. So at the time, I didn't understand this at all. It's only now when I stand back and look at it from a distance that I can see that was the case. And I feel we don't say that enough in our industry. That's the power, or community or universities. That's the real thing that's happening, right, when you're doing a PhD, becoming a postdoc, becoming a PhD researcher. I started my life as an academic, and I had other academics as models. I tried to be like them and reproduce their success. Wrote lots of papers, got grant funding, went to conferences, teaching, etc. And that all went very well. But then I moved to Xilinx in California, and that was completely random. I was not planning to go. It was just something they offered me, because and so many of the transitions have been totally random. the randomness in this transition was as follows. My partner at the time, she was doing a PhD, and she was Susan Spence. She worked in persistent Java. She stayed in the computer science department at the University of Glasgow. And so Susan was offered an internship at Sun Microsystems, where she was collaborating with this team at Sun that was working on this persistent Java programming language. So she was going to go for 3 months. And I thought, 3 months being away from Susan, how am I going to deal with that? So I contact my Edinburgh friends that make these FPGAs, and so by that time, we acquired by this company Xilinx, saying, come back to my friend John Gray. John, I need a job in Silicon Valley for 3 months so I can be with Susan. Can you arrange it? And so John pulls some strings, and I get to be an intern for 3 months at Xilinx. So I just go over, work for 3 months at Xilinx. I make some Photoshop accelerator using the cards and the plugin for Photoshop. So when you ran Photoshop, it did Gaussian blur and FPGAs, whatever. I did my project, waved them goodbye on the way out, and they just put a job offer in my hand when I left. I think it stopped me in my tracks, because I hadn't thought, but I thought I was going to be I was lucky to get a permanent position, after my PhD. I thought I was going to work at University of Glasgow forever. And, I thought it was quite exciting working on that accelerator, which I, used my a functional DSL in high school to do. And I joined solving a real problem, building an end-to-end system, because there's a lot of satisfaction for me to just, even writing the C++ code for the plugin for Adobe Photoshop and so on, just doing the whole thing from there to hitting Gaussian blur, getting the image, having it transferred to the over PCI to the card to DRAM, having the FPGA process it and getting results back and rendering the blur result to the user. That was fantastic. And I love the fact that when you do something end to end like that, you find out where all the dead bodies are buried. You find out where the real performance problems are, and I kind of like that. I like being able to do something concretely end to end. Where I think as an academic, I didn't have that luxury, right? Most of my job was not to do that, and I didn't have resources to do that, and there maybe wasn't a lot. I don't know what degree of scientific value that was to do it. So I thought, okay, this is quite exciting. Maybe I should do more of this end-to-end stuff. But I can't do it as a professor, right? I think I had to go to a company to do it. So I made the difficult decision to resign, which is very difficult, because I had postdocs, I had PhD students, I had government-funded projects, commitments to other people. To walk away from all of that was heart-wrenching. Some of these people I think are still not talking to me. And I joined Silicon Valley. And it was a big change. I was a junior academic, 7 years in at that time. I worked very hard. I did not have a lot of spare time, and I didn't earn very much money, and I was working hard to pay my mortgage. I arrived in Silicon Valley, and some people thought, this is going to be really hard. Yeah, you're in Silicon Valley, it's going to be super high stress. You were totally pressured. It was like a walk in the park. It was way less hard work and stress. I had like free evenings. I had to work out how to use a free evening. I didn't know what to do with one before. And I kind of thrived, I think, in this kind of Xilinx lab environment where I developed Lava and then went on to do lots of other things. So I love being at this intersection of solving really critical problems that people cared about, but bringing ideas and thinking from the world of PL and formal verification to bear down on that problem. And I had a very good manager who gave me the time and space to do that. And I think whenever I've had any kind of success somewhere, it's always not just been me. It's been things like having, imagine that case was Bill Carter, one of the early people who founded Xilinx. He kind of recognized the problem, the opportunity, and how to make me productive, and then created the environment to make that happen. So those are all my great managers have been like that. And all my terrible managers have tried to tell me what to do, and that never ends well.
So, speaking of terrible managers, you have a blog post about abuse and bullying in industry. I mean, this is a kind of taking a tangent here. I'd love, and I guess it resonated with many people. So I'd love to just tell us about it.
That's right. So, I mean, at one point in my career, I'm very fortunate. Most of my career, I've had great managers, and that's a lot. If I've had any success, I owe a lot of it to their mentorship and their help. But occasionally something goes wrong, and you get a manager and things don't work. And I had a particular, at one company, I had a particularly bad situation where I think I had a manager who I think was just maybe insecure, or I don't know why, but things didn't go well, and I tried to, try to go through HR to try and get this resolved. And I kind of learned a lot of lessons, because I think up until that point, I was listening to the company mantra, which was, we're human resources. We're here to help you. We're on your side. Tell us your problems. We're your friends. Even this term, human resources, I was amazed by this. When I arrived in California in 1998, someone said, "Oh, you'll have a meeting with human resources tomorrow." I said, oh, "Human resource? I'm surely you're joking. What's the real name of the department?" But no, it really was called human resources. And so I was tricked into thinking that they were on my side, but actually they're not. They're on the side of the company. They're the side of senior management. And when it comes to conflict, they're not your friends. And I ended up leaving that particular company after quite a lot of acrimony and stress and deep depression and anxiety on my part. And I think that was really tragic, because otherwise I was doing really well at a company. I think I was contributing a lot, and I enjoyed working with lots of people across the whole company. But this one clash, it was really, and I just learned a lot. I realized I was very naive about many aspects about how things like conflict is dealt with. Companies, why do people behave badly and do the things that they do, whatever. So I tried to write that up in this blog article. It was a few bits of advice, and it just snowballed. So many people email me and tell me their stories, or tell me they found the bits of advice I've given useful. People DM me when they see them in their town. I meet them for coffee, and I chat to them about what's happening. So people have really found that useful. And what it tells me is there's a market need for this, right? So when I posted this on X, on LinkedIn, it was like a lightning rod. It really, people kind of jumped on it, which makes me think, maybe as a community, we're not doing enough to honestly, seriously tackle, abuse in the workplace. And it's something we should talk more about, open more about. And I think another problem is this kind of LinkedIn culture where you just want to promote all the good things in your life, all the jobs that you got, all the successes you've had. You don't want to talk about your failures and things that are going wrong, or having to leave a job because you couldn't get on with your manager or whatever. The incentives are not set up like that. But we would be a bit of a healthier society if we were more honest about our vulnerabilities and what has worked for us and what has not worked for us.
Yeah, thanks for sharing this with us and with a lot of people.
Indeed, yeah. You got me fantasizing about starting a startup that's like a inverted world version of LinkedIn, when you're only allowed to post the hard things about life. Only the failures and frustrations go to the second.
I'd love to publish a resume which lists only the jobs I got rejected from, right, which will be way, way, way more impressive than what I actually got.
Okay, so on a somewhat more positive note, you're now at Groq, Groq with a Q, the machine learning accelerator startup company. I was wondering if you could just tell us what Groq is. What is the deal, and what attracted you here?
So Groq makes silicon chips for machine learning inference. So the chips have on them parallel systolic multipliers. So that's their big hammer. They can do matrix multiply very, very quickly, very efficiently, way more efficiently than a CPU. So a CPU doesn't have the computational intensity to hide memory access latency. So it's a latency machine. It does one thing very quickly. So if your job is you've got 17 totally different heterogeneous things to do, and you want to do each one of those things as quickly as possible, a latency machine is what you want. A CPU does that. If what you want to do is something like matrix multiply, well, that's quite computationally intensive. You need to get a lot of data right at your fingertips to get that matrix multiply going. The dirty secret about GPUs is they work by oversubscription to give enough computational intensity to these tensor cores to keep you busy, so that while you're doing that, you overlap that with the next memory access to DDR or HBM, and it arrives. And by the time you finish doing all those matrix multipliers, you've got your next one. And then you work on that. And then you hide memory access latency. That is why the leaders of Oracle and Twitter and so on are going to NVIDIA, right, begging for GPUs. We have a slightly different setup. So our chips, we've got fine-grained parallel multipliers, but we've also got lots of SRAM on our chip. 88 independent banks of SRAM, all of which you can access in one clock cycle. So phenomenal amounts of memory bandwidth. we have like a deterministic architecture. When you compile a model onto a chip, you know on every clock cycle what instructions will execute. That's like a mind-bending thing. When you compile a model, it produces an assembly file. The labels on the assembly instructions, the clock cycle that that instruction will execute in. Mind-bending, right? Almost nothing else that has this property. And this really helps us generate really efficient implementations of machine learning models. It helps us compose systems together to form big systems with predictable behavior and performance. So it's this co-location of this memory with the compute elements that gives them advantages, because the key thing that people care about today are transformers. Transformers, having them decoders, for example, Llama 370B has 80 decoders, which are all stacked next to each other. Inside of decoders, the computational element is attention. Attention involves multiplying some vectors, multiplying some big matrices. And there's an optimization called the KV cache optimization, which in this case turns these transformer computations from being matrix. No, that is memory bound, so it suits GPUs. So we can chunking away lots and lots of. You have the computational intensity, the mass memory access. It converts it from matrix to matrix vector. Matrix vector is compute bound. Now the GPUs are not in a good situation anymore because they don't have the computational intensity to hide the access to off-chip memory. But we have the KV cache there. It's in the SRAM. Nothing's going to go over a chip or a pin or a memory hierarchy to get to that data. So our co-location of compute with data makes us a great match for compute-bound computation. And that's why these things like Llama 3 and Gemma and Mistral really go fast on a chip, right? They have a very low latency, high throughput. So that's the kind of special thing about a chip. We can't get the whole KV cache onto one of our chips, but what we do is we break the KV cache up across many chips and nodes and multiple racks of a system. But because of our determinism, we still get good composability, low latency, very good throughput. So that's kind of the story of our company and why we're kind of doing well. So I mean, the chip design company, like I worked in design the second chip, which I think is about to announce. Sadly, in system Verilog, I couldn't get away with using Lava, and then I worked in its formal verification and some other aspects of it, and some aspects of the compiler as well. It's very exciting. It's very exciting stuff. Again, being able to work across the hardware-software boundary, I think is super exciting. And it reminds me a little bit of the 6502 because we're back to a world where cycle by cycle what's going to happen, and you try and exploit that property for various kinds of optimizations.
It's been full circle for you.
Since you mentioned it, Satnam, I can't help but ask. It makes total sense. Like a real chip company, obviously, System Verilog is going to be like the go-to choice, in the US at least. But like, how do you find the attitudes being in a chip company toward the idea of like new hardware languages? Is everyone like just fine with Verilog? Everything's fine, or is there like striving?
It's very hostile. So I've worked in 2 machine learning chips. In a very different way. I worked on one at Google, but that was a project which from day one, people decided we're going to use BlueSpec, which is this Haskell variant hard encryption language. And they hired people. This is the deal. This is BlueSpec. So we only hired people that knew BlueSpec, or were Haskell people we could repurpose as BlueSpec, or C++ people that we could brainwash into being Haskell people, and then we turned them into BlueSpec people. And that worked incredibly well. That we were a very small team, and we built a working chip in a small amount of time. I came back working first time, and that was fabulous. It was very, very, very rapid, quick production of a working chip. And I think we could do that again. I know of other people that are trying to do that again. But in Groq, for whatever reason, the people who are in control of the hardware wanted to use System Verilog because hardware engineers are very suspicious of abstraction, right? And they're very, very risk averse because it's a very risky business to make a chip. So, for example, even like having record types and interface reports, and you go, right, we can't have record types because it might cost us some silicon, or it might slow things down, or whatever. I don't know what's happening with these records. You're going, no, the records, it's like a pile-time abstraction. They evaporate. They have no cost whatsoever. But they still don't believe you, right? So if you can't have a record type in the port of your circuit, because doing dependent type, polymorphic, blah, 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 effect handler, really, they're going to call security and take your badge away and throw you in the building. So I think that's a shame. But if I could do my own hardware company, I would force people to use a more civilized hard description language, either BlueSpec or something, or a DSL that we make in some other language like Haskell or Camel or something like that. And then I would hire the right engineers. I'm not sure that the best way to design a chip is to hire people who are normal chip designers who know system Verilog. I think the best way to make a chip is to hire the best PL people you know, and retrain them how to do digital design. We did it in the first chip company work that we actually did quite a bit of that. And it reminds me of a trick a friend of mine played. Ian Pratt, he formed this company called ZenSource. They went on to do hypervisors, and he was in Cambridge, and he needed the cleverest programmers he could find. And this was his algorithm. He advertised in the Cambridge and London area for OCaml programmers. So people came and interviewed with OCaml code and stuff like that. And then when he got hired, they had to write this low-level C code. They're going, I'm not a C programmer. Well, you're very good at OCaml programming. I'm sure you could pick up C and you'd be good at it. And because they were just brilliant programmers. They were just very creative, brilliant people. And so that was his bait and switch trick. The way to get good C programmers was to hire good OCaml programmers. So I think there is something to be said for that.
So flipping the question here, like, are there problems that you see in, your chip design work where you're like, oh, I wish the PL community worked on this. Like maybe you've changed your views on what languages should look like, or other tools like static analysis.
I do actually. So when you do a real chip, you have at every level of abstraction, you have like a different view of the hierarchical decomposition of the chip, right? So when you are at the highest level, when you do logic design, you have got the hierarchical view of your chip, the top level block, the sub blocks, the other block, and how they're all connected and wired, right? And if you're a software engineer, I mean that hierarchical decomposition persists all the way to where the machine code is generated, modulo, cross-boundary code optimization, cross-module code optimization. Chips are not like that at all, because in the real chip, you also have power wires that distribute power, power and ground, wires that distribute a clock, and multiple clocks, wires that distribute enable signals, and so on. And so you when it comes to doing the physical design, you have quite a different hierarchical decomposition, which cares about how these global wires are fed through a chip and how things are laid out physically on the chip and organized. So that means the RTL code that the logical design engineers, right, they have this illusion of what the hierarchy is. The actual hierarchy and organization of what get turned into gates is very, very different from that. And the design process is sequential. You have to do logic design and freeze it. Then you do these other verification and physical design things. And then then it's very hard to go back and make a change if you want to, because probably somebody manually or through some tools mutated and reorganized your design. You've kind of lost the link right from the original code you were in. It'd be great if we could have programming language support for describing different types of hierarchical decomposition and keeping them in check, right, in sync. So you can then go forward and backwards between them to give you, it's a one program, it's a one circuit, but you want to have different views of it. So I think that'd be cool. Yeah. I don't know anything that does that.
That would be incredibly cool. I can't help but note it sounds really hard to do in the current landscape of hardware tools that are closed source and extremely expensive.
Yeah.
It's like something's got to shift to sort of like let academics get like the access to the levels of abstractions they need to do this.
I'm a big fan of the people that do, Verilator, the people that do Yosys HQ. So the form of verification work that we do, our company uses the Yosys HQ tools, which are then, based on Verilator and Z3 and CVC. I mean, mainly because we can't afford Jasper Gold, the heavyweight industry standard tool. But I'm quite impressed by what they do, and I think if that, ecosystem could get more traction, more support from other companies or universities. I think it's great stuff that could be. I think it's great stuff that could happen. And there's various research groups around the world that do great things. I mean, like yours, great stuff happening. I think at Cambridge and Tobias Gross's group with like fantastic stuff like lean MLIR, two worlds that were previously separate in my mind, clashing together. So if there's some way to like coordinate all these things into kind of like a wider master vision of how the world of chip design could be different, I think that there really is an opportunity and need there, because nobody really likes what they have at the moment. Like the real hardware engineers refuse to use any of these other tools, but also hate the tools that they have.
Yeah, it's kind of bleak when you put it that way, I guess.
I mean, another strange transition I made was, I think the transition from University of Glasgow to Xilinx was, it changed one axis. I went from academia to industry, but it kept another axis constant because I joined the newly from Xilinx Labs. So I still wrote papers, I went to conferences, I was in a kind of program committee. So I still kind of behaved a bit like a researcher, applied researcher. But the most stark change I made was when I left Microsoft Research Cambridge, where I very much behaved like a researcher. My job was to be Satnam, which was a very nice job to have. I think I'm good at that. To joining Google in Silicon Valley, where I was just a software engineer and I had to write code for distributed systems, and it was a big shock. I learned then that I could not code. Even though I'd been coding my entire life, and I'd written, I don't know, millions of lines of code or whatever, I'd never had to write code as a professional software engineer for a production project with deadlines and so on. So the whole process of code review and everything, that was all kind of like new for me. In my research projects, I never had to do that. So yeah, I had this fantastic TL, Daniel Spoonhour, a PL person who did his PhD with Bob Huffer at CMU, and I had my peers all over half my age, and I learned from. They taught me how to become a professional software engineer. So a very humiliating process, but I'm very thankful and grateful for it. And I think I went on to be a pretty decent Google engineer, and accumulated right and working, being one of the early people in Kubernetes, which is bizarrely the most successful thing I've done in my entire career. Utterly unrepresentative of everything else I've done. So that was a difficult journey, the most stark, right? Because all the bits kind of flipped, right? I went from a research world to production, DevOps, or with a pager. So that was a difficult transition.
Do you have moments where you were like, "Oh my God, what have I done?" Like,
absolutely. Except for, well, before I decided what I was going to do. I decided what projects I was going to do, and I took my time to do. I could write in Haskell or F# or whatever, and I went. And I was in control of my destiny, and I wrote my own code. I didn't have to have my code reviewed. I just, it's like research code at MSR. You check it in. To getting 4 lines of code checked could take a week. And I thought, what have I done here? This is, but I stuck with it, and it was great. I think I learned. I think I learned a lot, and then eventually I loved being a Google engineer. I mean, I don't work at Google anymore. I've worked for Google twice so far. I enjoyed being a Google engineer, and I identify, even though I don't work at Google, I identify being a Google engineer, other Google engineers. It was a very useful experience and taught me much about software and how to write software in a social manner, in a way that's kind of durable, it can be evolved, that's reliable, that's scalable. Things I've never really had to do before. And those turned out to be like very useful kind of life skills. I'm a 58-year-old man. I'm still write code and design circuits every day for a living. I think if I had not been through that process, I'd probably just be a VP drawing boxes and arrows and writing documents. And that's not what
So we wanted since you've been in industry for a while, but you've kept ties with academia. I see like in your CV, like every once in a while, you do a visiting lecture gig or teach a course, something like that. How like what attracts you to doing that? It's way more work having 2 jobs.
I always loved teaching. I remember at the beginning of this podcast, I talked about how inspired I felt by my professors and how they taught, how amazing that was. So I've always wanted to be like that as well. So I've always enjoyed teaching, trying to explain things, giving examples, writing demos of code around them. So I always try to do a bit of that. So when I worked for Microsoft in Redmond, when I lived in Seattle, I also was lucky to have an affiliate position at the University of Washington, and at the electrical engineering department, I taught a course on how to test VLSI chips, and that was fabulous. I loved doing that. When I was at MSR Cambridge, I actually had a 20% appointment as a professor at the University of Birmingham, and I gave some lectures there, and a nice research group to hang out with. And I was a visiting lecturer at Imperial College. I would rock up every now and then and talk to PhD students. I love that, and I especially love just talking to PhD students and postdocs and giving just a different perspective on their project and their direction from their advisor. I think they learn a little bit. I learn a little bit from them about what they're doing. And then here in the Bay Area, San Francisco Bay Area, where I was lucky to be connected up with the Lindsay Cooper crowd and teach a course in Verilog hardware design at UC Santa Cruz, which was okay. I taught that course during the pandemic, so my screen was a grid of black rectangles, and the University of California says I'm not allowed to make the students turn their cameras on. So that was a bit of a dispiriting experience. When I was offered to do it again, I declined. And it made me realize how much I love being in the room with the students and teaching as a kind of a two-way kind of thing. And I didn't like teaching to an array of black workspaces. So yeah, it just gives me like lots of energy. I think it's one of the sources of creative energy for me is going to these places, talking to the students, giving the talks, getting feedback, learning what other people are thinking and working on, and what excites them. I really miss the collegiate atmosphere of a university department. That's something I miss the most from the University of Glasgow. All the other research groups, banging into with someone in the corridor and having a chat about some related thing, all the great invited speakers coming in. I think that's a fabulous, very special thing. And I've never really experienced that, even in research labs. So I never really experienced that in industry. That's one thing I'm very jealous about from my academic colleagues. So I try and, whenever I can, find an excuse to turn up at university and give a talk and hang out with some cool people.
Yeah.
Can you tell us your time management tips? How do you manage to do both at once?
Well, I mean, I don't do very much of these things. So I taught a Verilog course. So then I think it was just one course that I taught. I taught half of it. It was somebody else taught the other half. So I would just say that was like a giant amount of time commitment. And then for the visiting other people, I always collocate that with some trip I'm doing anyway, right? So if I'm going to a conference, giving a talk, then I'll tackle that one. So on Monday and Tuesday, I gave a talk at a new computer architecture conference in London called Reach 2024. So I was in London, so I extended my visit by one day, and I went to Imperial College. I spoke to Ali Donaldson saying, Ali, do you want me to turn up and give a talk? And Ali said, okay. And he made gave a talk there. And then before I went to Reach, I stopped over Chicago and gave a talk at Purdue. So I tried to tack them on to other trips that I'm doing anyway. So it definitely takes up a chunk of my time, and my productivity at work is definitely lower as a result of it. But I value it enough. I think I get enough out of it, and it gives me enough kind of creative energy and inspiration for other things that I might tackle at work that I feel like it's worth doing.
So you mentioned at the beginning that you were, you for a while you were a physics student, and physics has a lot of kind of open existential questions, right? Like the theory of everything and the standard model and what have you. Is there such a thing in PL? And if so, like what is it? Like, is that what attracted you to PL? Was there some like existential question?
Yeah, I'm not sure if I thought about it in that way, but I think that there's definitely something about language, having a language to talk about the world, and having a language to model the world. And then when you have that model, it's interactive. It could do things. You could do experiments with that. And so that, I think it goes back to what I said at the beginning, where this wonderful synergy between functions, recursive functions, lazy evaluation, and how digital circuits kind of work. And that just seems like a magical thing to me. And I mean, some people use programming languages because they have to get their jobs done. When I talk to my friends who are systems researchers, they'll write in C or C++, and it's just to get the job done because they have to run an experiment and get a graph and a chart. And the program is it's just like something you have to do, some side effect to getting your job done. I think programs are beautiful. I view them in the same spectrum as literature and poetry or whatever, because they exist there to help us communicate ideas from one person's head to another person's head, from a person's head to a machine to maybe another person's head or whatever. And I kind of I'm not sure I entirely believe it, but there's a little bit of truth and beauty that I kind of really believe in. So I feel if you can have the right abstractions and mechanisms in your programs to then model something in the world in some way, you've kind of captured, something kind of truthful, right? So that
universal language where everyone can understand it. Agree to the semantics of it.
And so I just love programs for how they are, for the beauty. I don't even care if you run them; they just look so beautiful, and that's what I kind of love about kind of Haskell and these kind of lovely kind of types, and it's the aesthetics of the I value the programs for themselves.
Yeah, and I guess because of that, you want to build an FP castle. And so maybe tell our audience about this idea.
Yeah, I have this dream of hopefully Groq will come enormously wealthy, and I'll have enough money to then buy a castle in Scotland. And what I want to do is I want to do something a little bit kind of like Dagstall, but but the scope is like a year or longer, and I want to invite people to this remote castle to come and hang out and do functional programming, do C++, do systems, be a jazz pianist, whatever, have some paintings, whatever, where people just are in a remote part of Scotland with beautiful scenery, inspiring background, and you don't necessarily need to be computer science, but people are there for extended period of time, interacting with each other, learning from each other, being inspired with each other, and it could be through poetry, could be through music, could be through could be coding. I plan to do a lot of cooking. We'll have a whiskey cellar and cook lots of nice meals. I think that'd be quite nice to have a kind of a jamming session like that for a kind of a bohemian jamming session lasting about a year. So that's FP Castle. You can go to fpcastle.com and sign up. You could just create a PR and GitHub and send it to me.
Oh, nice. Yeah. Okay. I'm gonna sign up. Yeah.
Yeah, everyone listening is to go to fpcastle.com and sign up.
The rooms are running out.
Right.
Cool. So I guess should we talk about food? So you're well known to be a foodie. Is that do you go with that term, or is that
I'm happy to say foodie. I mean these are cookbooks, and I've got more.
Okay.
Right? Not of these, you might think they're computing books, but every single one of us is a cookbook. So I love food. I love cooking, and I think it's just a wonderful way to interact with other people. I got into cooking through someone I met at university who also used cooking as a social vehicle, and everyone who for relaxation, everyone seeks some kind of task that they can be totally absorbed in, so they can relax from work and detach. And for me, it's like cooking, trying to cook a nice meal, inviting friends around and having a nice food and nice wine over a nice evening. So I do a lot of that. I cook, I do many dinner parties. I actually have a cooking log. A cooking log goes back decades. It's now a digital document. I record who came for dinner, what I cooked, what worked, what didn't work, who got on with who didn't get on with who. There's a separate secret document, which is the incompatibility matrix, which shows which guests are incompatible with other guests. So I take it kind of seriously, and I kind of I love it's one of the main ways I interact and socialize with other people. And when I go to conferences, I try and get people together and go out to nice dinners, because it's a nice informal way to get to know other people and interact and socialize with them. So yeah, it's become a big part of my life and my identity, especially my identity in social media.
Yeah. So what is your favorite restaurant? So we can do like
my favorite restaurant is called
question.
It's in Glasgow. So my daughter, she's a final year computer science student at the University of Strathclyde, taught by many of my friends. And downstairs from her is a restaurant called Brett, which does just fabulous sort of Scottish inspired food. I mean, it doesn't have a Michelin star or anything like that, but it's just like really great produce, wonderful scallops. They cook beetroot amazingly. They'll do fantastic things with a mushroom, and they have great organic wine selection. So it's just like informal setting, gorgeous food, happens to be just downstairs from my daughter's apartment, or maybe my daughter's apartment just happens to be upstairs from the restaurant. So I love that place a lot. So if you go to Scotland or you go to Glasgow, I really recommend going to Brett. I mean, I can list plenty of Michelin-starred restaurants that I went to where I've had wonderful meals, and they're all fantastic as well. But I think it's always great when you can find something that it doesn't have stars, but it's still really good and a bit more informal because I don't need all the posh aspects that go with posh restaurants.
How about a favorite cookbook? Got one?
Well, I have it here. It's called Noppy. And it's a cookbook of his restaurant called Noppy that I ate at on Wednesday night in London with my daughter. And it's my most used cookbook. You can see it's like falling apart. And it's like if you come for a fancy dinner at my house, there's a good chance that I will, cook out of this book for you. I love it. So a lot of artillery books have kind of fairly straightforward recipes. This one has a warning at the front saying, make sure that you really are the kind of person that's up for cooking the recipes in this book, because they're all a lot of them are quite technical and complicated, take many days to do. But I've cooked many of the recipes out there, so it's always interesting when I eat at there. So on Wednesday I was at the restaurant, so I was getting things somewhat similar to what's in the book. So it's always interesting to see, did I get it right, or how different was it from the standard version. So I think that's fabulous. It's a fabulous cookbook. I love. I've been cooking from it for a decade almost.
And since you're Scottish, what's your favorite scotch?
Well, my favorite bottle is this one called Octomore.
Oh, I've never seen that.
And this bottle sadly is empty. But it's a very, very special bottle. So many people who drink whiskey or into whiskey, they will know that there's a brand of whiskey called Octomore. And you can buy an Octomore today. But the Octomores you get today have really kind of diverged. So this is the first batch of Octomore that was ever made. And this bottle was given to me by a very good friend of mine, Rolf. And he bought futures in the first batch of Octomores. He bought 12 bottles and he gave me one. And this comes from a distillery called Buchladich on Islay, which is known for its smoky whiskies like Lagavulin, Ardbeg, and what happened was someone bought this distillery and they looked at their stock, some of which was terrible, some was okay, and they've tried to salvage some whiskies and blend with other whiskies to try other barrels to kind of reboot the whiskey and kind of rebrand it. And Octomore was one of the first things of that project that they did. And it was just absolutely fabulous. I remember my first sip. I remember where I was sitting, where I had it. It was absolutely mind-blowingly excellent. It was, and again, very much a very smoky, peaty whiskey, but just absolutely exquisite in its taste. It's gone now. I don't think you get any more of that V1 Octomore. So now we're into V. I can't remember where it is. The current Octomore is a very, very astringent, very, very smoky, very 240 parts per million. Still very, very good, but I don't think they have the kind of delicacy and balance of this original Octomore. So this was, I think, the best whiskey I've ever had. Sadly gone.
The current Octomore seems to be 14.2 for what it's worth.
You're right.
So beyond those recommendations, thank you, by the way. I mean, you're checking out all of these things. We have again saved our most difficult question for last, which is, what advice do you have for younger researchers than you? Say, like, let's to keep it concrete, let's say to graduate students and to undergraduates. What advice would you give to them?
Yeah, so maybe I'll just do a little bit of a repeat of what I said earlier, which is to have a broader view of what you are doing. Like when you do a PhD, things are very narrow and they're very laser focused, and often you can kind of think, well, why am I doing this esoteric thing with this weird type system or whatever? What good can ever come out of this, and will anyone ever care? But what's really happening is you're learning how to think, you're learning how to read, assimilate information, and then categorize information and compare one thing to another, do an evaluation and judgment, then express yourself by trying to write a paper or evaluation or give a talk to someone else, and then try to collaborate with someone else to try and solve this bit of the problem. And although you're doing these things for a particular thing, you're really sharpening these tools you have to be a general problem solver, and you're just developing a toolkit for thought and problem solving, which was wide applicability across all computer science and beyond computers, probably your personal life and many other things that you have to do in the world as well. So I would say kind of hang on to that, because I know, from my own personal experience, when you're really deep down, very deep in one esoteric thing, it could be dispiriting. You think, why am I doing this? Why does anyone actually care? Think about the second and third order effects of what's actually happening. And I mean, I would cite myself as an example of that, right? I did all this kind of esoteric stuff, right, with Miranda and everything, non-standard interpretation and lattices and things like that. But yet, it proved useful in quite a diverse areas of computing science.
Wonderful. Well, thank you so much for taking the time.
Yeah, thank you, Satnam. This is really wonderful. I really appreciate it.
Thank you very much for inviting me. It's been good fun.